Okay, so hello everyone. So I would like to present today our speaker, Dr. Bartek. Sorry, I don't want to butcher your name by pronouncing your name wrongly, but we have Dr. Bartek over here from Lublin University of Technology. He has been a very long-term collaborator with Professor Bartek, and we have worked together previously as well. And today, I let the stage present.
Okay, so Rohit, thanks for the introduction. Okay, so we can now go on. So I will just read out my full name. So my name is Bartłomiej Ambrożkiewicz. This is my full name. So I know that it's pretty hard. Yes, as Rohit knows me, I'm called Bartek. Yes, it's an abbreviation of my name. Okay, so just first few words about my activity, scientific activity. Yes, I will refer to this what Rohit said, that I'm collaborating. Actually, my supervisor, I think you know him well, so was Professor Grzegorz Litak. Yes, one of the, I would say, masters in nonlinear dynamics, and actually he was my supervisor of my all thesis. So actually, like engineering thesis, yes, and finishing with a PhD. And actually, yes, so actually, this is actually just 4 years when I was here last year, when I was here for the first time, actually, in Ireland, in Dublin. And yes, and what I said, I'm just collaborating also with the group, with your group, especially with Rohit, Asifa, and Professor Vikram Bakrashi. Okay, so regarding my scientific activity, so this is the topic of my presentation, is actually the application of artificial intelligence in the diagnostics of rotational systems. And what I haven't mentioned, that I'm just assistant professor at Lublin University of Technology. So this Lublin is actually southeast, it's a quite big city in the direction of southeast from Warsaw. Yes, and I'm working now at the Faculty of Mathematics and Information Technology. Okay, so first words about the rotational systems. Yes, this is where I grow up with scientifically, what I was doing for my professional job, and later on I moved on to the scientific one. So actually, rotational systems you can see it everywhere. Yes, we use them, and maybe not directly, but indirectly in many ways, in the bus, in the lifts, everywhere. Yeah, so here I'm just showing the examples of rotational systems, so like a turbine engine, like electric motor, like a ball bearing, and hydraulic pumping, for example. So this is somehow what I'm dealing with, especially with the ball bearings, because I'm from the city who is famous for one of the most famous ball bearing manufacturer, and I was starting a professional career there. Later on, moving it to the science. Also, yes, as the first slides, yes, I would like to refer to the, let's say, like basics, fundamentals, just the introduction to the topic, yes. Another issue that I'm doing is actually predictive maintenance, yes. So it's actually the next step of the theory of reliability, not only just referring to the, let's say, the classical reliability of theory based on the theory of reliability, but predictive maintenance is actually what is done in time, yes, in real time. So actually, I mean the diagnostics in the real time. So just to predict the time of failure based on the real time data analysis. And one of the goals is just to have the optimization of the maintenance schedule, minimize downtime, and extend the lifespan of the equipment. Yes. So, but we refer to the, let's say, to the data that are going on, and we will observe what is happening with, for example, like some factors, yes, statistical factors even, yes, who calculating the specific features in the time window. Another issue is the predictive maintenance. Yes, actually, I mean, yes, continuing this. So actually, we can specify like historically, we can specify 4 different, let's say, type of maintenances. So the first one was reactive. Yes, if something got damaged, we have replaced it. We have made a replacement for that. The later one the next one, starting from the is the preventive maintenance, which came from the scheduling of the in aviation mostly. Yes, based on the based on the scheduling of the of maintenance of mainly plane components. Now we are at the stage of the predictive maintenance, I would say. So now we referring to the real-time data, and also based somehow to specify the model on the historical data. We have a predictive maintenance right now, and the next step, which is actually now mostly in the science, is the prescriptive maintenance. So actually, AI gives us some information what can happen in some time. Yes, so like predictive maintenance, for example, we have a one feature, for example, like RMS value, and when everything is fine, is on the constant level. Yeah, so we calculate each one by one. So we calculate one by one, and yes, we are under the level of the damage. Once something had happened, it propagates, and this RMS value, because of the increased energy in the signal, is also increasing. Yes. So what are the advantages of predictive maintenance? Yes. So first of all, first of them is actually reduction of maintenance costs. Yes. So it reduces maintenance costs and unnecessary part replacements. Yes. We can just it's like one of the methods of the scheduling. So just-in-time methods. So we can just monitor the condition in the real time. Of course, greater operational efficiency. Yes, so machines can operate in optimal conditions, which increases productivity. Reduction of repair time, of course. So we can just refer to the specific faulty part and just to have a replacement into that. So we don't have to make for example, the monitoring of the whole production line, but we make it, yes, but we know where something happened. Of course, everything, well, like the better control of the process, actually, it helps us to avoid problems resulting from faulty components. So what improves the production quality. And the last, actually, it's for the case of the companies. So it's for also just we can reduce the downtime and cost improvement for business profitability. Actually, combining the predictive maintenance, what I'm doing actually, combining, of course, with the signal processing, of course. So I mentioned about the different features. I mean, statistical features that can be calculated in time, and just based on them, we can refer to the specific results. Actually, we can have an optimization. And actually, the signal processing diagnostics, yes, so it helps us to identify and classify the system operating states. Yes, so as you can see here at this graph. So for example, here is a pointer. Oh, maybe I just don't want to interrupt. So you can have it just, for example, like a time healthy state. So for example, RMS is low enough, just not going over this limit. Yes, when it starts, as I told you, as something is there is some failure in the system. So the whole total energy in the signal will be increasing, and it will go. This value will go over this limit. Yes, here are also another examples of the let's say where this signal processing can be used as well. I mean signal processing, but also different methods. Yes, for example, like FEM methods, or just based on the combination of the normative methods and also FEM methods. So like this. The standard approach, yes, that is used. So of course we have a sensor. Later on we have a signal acquisition of course from the system. We do some signal processing. We make a diagnosis and decision on maintenance. So just this is for the, let's say, for an introduction, and I will refer to my research. Yeah, so actually, what can be also the source and main source of the information which is embedded into the signal. So, for example, like we can just monitor the temperature. Of course, with something at failure, we have a higher torque. We have of course. So what will go with the increased temperature. Of course, noise as well. So as another source. So, for example, like in acoustic emission method, voltage. For example, like we refer to the piezo sensors. So of course, the voltage can be also this source of information, and vibrations, for example, like acceleration of vibrations, for example, monitored with accelerometers. Okay, so the first, I would say, the first system that I would like to introduce to you is actually EPIC module. Actually, I discussed with Asifa and also with Rohit what is this actually. But do you know what is EPIC module or not? To the others? No. So you in the car you have a traditional handbrake. In most of the cars, so you have a traditional handbrake, which is based like on wire, right? And hydraulic system, of course. But this one is also, yes, it's referred to, of course, hydraulic system, but this is actually electronic one. So this system, for example, like we have here we have a lot of high velocity over here, and going to the pressure and just on the clamps. So this this small system, which is I would say maybe like I put into two hands, is responsible just for the blockage of the system, yes, of the braking system in the car. Yes, so this is electronic one. Actually, however, because this is the cooperation with one of the local companies, I mean local companies. This is the Danish company in Lublin, but the site located in Lublin is dealing with the regeneration of those systems. So these systems, as you can see, it's way complicated. So we have a couple of shafts, we have a couple of gears, but I will just show you just the photos in a moment of the real one. So this is also the real system. Everything was based on the mesh of the gears. But I will just show you what can be the failures of this. Of course, these systems can face some different failures, of course, and this is sent to remanufacturer. This is in this case a Borg Automotive company with whom I'm cooperating with. And especially in this area, the diagnostics of those systems. Yes, that was quite new solution. This is actually, as you can see in my hand, this is one of the EPIC modules. So we have a standard connector, so like a 12 volts. However, this is, as you can see over here, this is actually glued with two parts of the housing, and this side everything is closed. Yes, so we have a connector, we have electric motor combined with one of the pinions. Pinion is interconnected with the planetary gearbox for a high pressure force, and it acts on the brake calipers. This is what is outside actually of this system. However, what is inside is actually I'm just referring to the failure modes. Yes, but when you open up the upper part, so you can see there are a couple of things which are inside. Yes, so below this pinion, so there is an electric motor combined with the mesh, and also by this tooth belt with the planetary gearbox that is going out. So, and actually here I want to refer to some failure modes that we have. Those are real, but some of them we have just generated. For example, we have a wrong mesh, so the tooth belt is sliding over the mesh. One of the missing gearbox. It will work, but it will not generate the same power outside. Of course, there is also this is the, I would say, bottom side of the electric motor. So we have one failure with no damper and of course damper. Yes, so I also simulate that. For example, this rubber is, for example, all that it doesn't have so elastic, so it also generates vibrations. Of course, this is actually cracked a little bit and the tooth belt. Also, there can be it's not visible. So somehow that one of the tooth of the pinions can be cracked as well. So this can face different, let's say, failures. Somehow it goes about the system that we have used. It was a simple system for the measurement of the vibrations of the system. This is actually what is happening in the lab, but it's just because it's on some housing that was what we don't sometimes on the like a stable position of that. So of course you've got of course source of voltage. Yes, so 12 volts. Like you have 12 volts in the car, interconnected to the EPV system, and piezo sensors are where the three different locations. I'll just refer to the moment. Everything was collected with the data vibrations was collected with the data acquisition card, and I was using FlexLogger software for the data collection. Of course, so as I told you about the piezoelectric sensors, yes, we were looking for some solution because actually this is actually the first step as the characteristic frequencies, and actually this system itself it's not so recognized. You will not. When I was preparing my first paper, I couldn't find some analysis about the vibroacoustics of the system. And what was the origin, yes, of this idea? Because the company was facing, so when they got this part for the regeneration, they got it like this, so worn out, but they didn't know what happened inside. To be honest, where to look for the solution, where to look for the failure, what could happen. So as we were using the non-destructive testing, so we were using the piezo sensors aligned to the housing in the different parts of the system, and this is what we wanted to do. Where we should look for the solution. Yes, for example, it can be a failure of the motor, but we could omit it. But for the first time, we have tried. We have installed it on the pinion and on the gearbox. Yes, on the gearbox, planetary gearbox on the height of planetary gearbox. And this is how we recorded the vibrations of the system. So if it was about what we have used, so I mentioned about the piezoelectric sensor, and I'm in the right place because I are dealing also with those sensors like this. So of course, I don't need to actually introduce you so much, but when you press it, so during the crystallization, during the pressure, during the crystallization of the semiconductor material, so the voltage is growing. Going up, is growing. Yeah, so this is somehow what we use. And actually, in case of this system, so when we have a constant voltage, yes, 12 volts, so the velocity of this system was constant all the time. Yes, so because actually you don't need to control it. Actually, those are the let's say such a movement with the electric brake. It's really short, let's say, really short operation, I would say. Yeah. So actually, in the short time, you need to find what happens. Yes, maybe I will also skip it, just refer it. But where you have the piezoelectric effect. Yes. So as Asifa mentioned, so we are using it for the control for the deflection of the beam. Yes. So this is one of the cases. It's really sensitive material, and that's it. Normally, it was used for example, in the lighters or in the ovens. Yes, that was also was shown to my students, but we have also prepared the digital demonstrator of this system, but now it's like for some companies, and as we have what we have recorded here, so it was like a diagnostics. Those are the output signals, let's say, from the placement where we have mounted the piezoelectric sensors. So like on electric motor, on the pinion, and planetary gearbox. From this perspective, you will not see anything. Yes, so this is actually just the signal just in time. Yes, so what happens in the time domain. But as I mentioned to you about the calculation of some features. Yeah, so this is how somehow what has been done. And going to the workflow, yes, of this analysis. So first, of course, we have a like a different kind of we have the different let's say failure modes inside. I mentioned about the failure modes, about the preparation system. So we have done the voltage measure. And if it goes about the feature extraction, what we have used, just some of them are familiar, I think, to you. Of course, like a mean, median, RMS, totality, skewness, peak to peak, crest factor, shape factor, and those are higher moments like FM4 and M6A, for example. Those features were introduced last, I think, but it works like an impulse factor, for example, like clearance factor, and so on. I didn't make a description here, yes, but actually here are actually the levels of the what is this actually on x axis. So on x-axis we have the number of the window. Yes, so we have a long-term signal made of this analysis. So it was every failure mode was recorded by 30 seconds by 30 times. So in total it was like one signal, it was like a 25,000 data, because it was consisting of around 25,000 data points. So every 30 seconds we were stopping it, and we repeated with the same failure modes. Yes, up to 30 samples, 30 patterns. So in total, it was I think around 700,000 repetitions. Sorry, data points. I mean, and this long signal consisting of 70,000 data points was later on dividing into like a 4,000 data points window, and we were making like a sliding window analysis. So we was like from the first data point to 4,000, 4,001 to 8,000, 8,001, 12,000, and so on and so on. Actually, and those are the results how this feature was changing in time. Some of them were growing, some of them not. However, just to observe if we have some limits, or just the results of the features are just in some limits, or each failure can be assigned. However, more this I have also this paper, but I have also grouped those failures into like a group into the groups. So the failures coming from the electric motor, failures coming from the gears, and the others. But I will show you at the end of the presentation. I will show you as well this paper where we have published. And everything was and the next step was using a couple of different machine learning methods, just to observe if those failures they are not mixing. We have a good, let's say, assignment, a good of the data. Yes, about machine learning models, just the two slides about how we use them. So of course it goes about predictive going. So as I have an example, so we have, for example, like red ball or just blue ball are just the two different, let's say, values of the feature, and they can be assigned to one group or another one. Yes. So the most interesting thing is, of course, here. Yes, where those two classes are mixing, and we can have like a misclassification. So like the blue one was assigned to the red one, and yes, so this is like a made of nearest neighbors methodology. Of course, one thing about the neural networks, yes, we have different layers and so on, but as I remember well, actually tree-based models worked the best in this solution. So as we have like a data, like a sort of data, I mean like a group of data, and it can be it's very simple, as like we have a diameter, size, and color. But in case of those data, they can be classified by the limits of the data. So this is it. And if it goes about the results, yeah. So this so every let's say confusion matrix represents the place where this sensor was mounted. So on electric motor, pin gearbox, and actually it's doubled. But if it goes about the best results we have obtained from the planetary gearbox. So this one, this is not an opinion. And an opinion on this. Also, the classification was really nice, but it was the hardest just to distribute we got the highest number of misclassification from the sensor mounted on the electric motor, and this is what we could also face, or actually we could expect. Actually, I mean, because actually the problem was that. Let's say, as you could observe on the time series over here, it was on the constant level somehow. It was noised, but it was on a constant level somehow. So somehow that was the first results from the regarding the diagnostics of EPB module. Another topic that I was running, and that was the part of my PhD, is the extension of this research. So moving also this AI part, so that was analysis of radar internal clearance of bearings. Here is actually the definition what the clearance is. Yes, this is not a failure. That somehow kind of thing, but radar clearance is actually operational parameter, which is always in the bearing. So as the definition says, is the key operating parameter of rolling bearings is the internal clearance, which means the permissible movement between the bearings rings, radar in ball bearings or axial in tapered roller bearings, and it refers to the impact on the service life of bearings, vibration characteristics, and heat generation. So this is actually this distance, this small distance between the poles and between the ring. So this is somehow we can just specify three of them. Initial one, when you buy a bearing, you have predefined clearance. When you mount it, there is an interference fit, so it's just decreasing a little bit. Yes, after mounting. And operating clearance, when everything starts to operate, we have a warp expansion on the internal link, on the internal link, and it shows it's not blocking, but I mean it's expanding, and this clearance is decreasing as well. So this is how the bearings was mounted on my experiment. So for example, when I put it, we have an axial nut over it, and it was possible to control clearance as well. Because actually, because of the first comments of the reviewers of the first papers, it told us that we need to keep the constant conditions of the experiment. So those were the two different test rigs that I have used for my experiment and also for my PhD. The first one was actually the PhD of my colleague, but we have used it over here. We had the bearing, and that was the automated systems for the measuring the radar internal clearance in bearings. Yes, so we're pressing it with the axial nut, and we could measure what is the clearance inside with the, so like this. And in one bearing, what I showed you then, because the cone over here is tapered cone over here, so it's not like a flat one. It's tapered. So it was possible to put for example, like initial one. So just to put the axial and just block it, but we kept the clearance that was like a mounted one. Yes. During the test, we have learned also what is the thermal expansion because of the linear expansion of the metals was possible as well. It was approximate because this, of course, this internal ring is rotating. This one is fixed. But in the one bearing, we were able just to put the pressure with a nut on the face of the bearing, and just to reduce to have a harder reduction of the mounted clearance. Yeah, so this somehow we could start it up. So we had a different clearance groups as well. Okay, and after the measurement and the setting of the clearance inside, we will put, because this is actually this part. So like this bearing is closed inside it. So in this housing, this part you can see is behind this part of the shaft, just connected with the coupling, is behind it. Yeah, so this is somehow how it was mounted. So it was like shifted like this, and we have used two accelerometers. We have used two accelerometers to have a measurement of the clearance. Also, those were piezo sensors. One was piezo and one was I forgot actually. But this number two, and we have used it. It was a piezo sensor as well, but it was let's say certified by the company IFM, by the German company IFM. So those were the signals. And actually, you can see here, actually, this is the predefined radial internal clearance, like a 48, 25, 8. But it was all the time we have referred to one bearing. Yes, so we can omit what are the how inside how it's produced inside, because actually we can have also an impact of the from the undulations on the raceway. So this is somehow why we have used one bearing, but I mean one bearing. Later on, it was also referred to the others, but such a reduction we wanted to have in one bearing, not like a predefined, like initial one, but just one this way. Also, if it goes about the workflow, it's really similar. Yes, so we have like two systems. We have acceleration measurement, and we were comparing to approach. So the raw acceleration signal without the denoising, and with variation about decomposition. So the first few modes were used only for the analysis. So the let's say small amplitude modes were omitted. It was like somehow like a denoising the like a filtering, somehow we can say. Of course, because of feature extraction, those were similar. The methods of machine learning methods as well were similar. And this is how it was much more complicated. Actually, bearings, if it goes about the diagnostics of bearings, it goes about the failures. Yes, about if we have for example, crack or just a failure on the specific raceway, it can be described by the empirically by formulas. But in this case, it goes about the clearance. You don't have the reference to that, but somehow it introduces the non-linearity of this to this system. And of course, those were two approaches. One with based on the variational mode decomposition that we have been used, and before noise. Yes, and here are the clearance classes, like a C2L. So it's a C2 lower C2 class. Yes, normal clearance, C2 upper, C3, C4. But it refers to the specific values of the clearance, like a 48, 25, 8, and so on. Yes, so but it goes from them. And here actually are the results For example, like gradient boosting, yes, because actually there were not comparison between the classes, but also by those classes, but also for the specific velocity, yes. So it was easier just to make to have this confusion to get this confusion matrix by lower velocity than the higher one. Yes, so it was by 10 hertz rotation. So what corresponds to the 600 RPMs in the system, because actually it was AC current motor, and actually we had so we were able to make some tests up to 50 hertz. Yes, so up to 3000 RPMs, but that was pretty enough just to test those bearings, because those were pretty big one, not for electric motors, which are rotating like a much more for example, like a 20, 30, 40,000 RPMs. And actually, if it goes about acknowledgements, so yes, because actually, if it goes about my PhD, I had a cooperation with the NTM SMR company. It's a French-Japanese company. Actually, this is the Bulgarian manufacturing, and Borg Automotive is the company that I'm still cooperating with regarding the analysis, the diagnostics of the EPB models. Actually, Borg Automotive, for this method, we got the patent as well. So actually, this is the first step. But the next step is just to get the product, just to produce the machine, which will make it automatically. So based on also analysis, but make it automated. Maybe even to use such a system like IFM system, but mount the system, put it automatically just to align the sensors. And after the rotation, based on the dynamics, we could get to know what failure is inside. Just a couple of slides about the Lublin University of Technology. So as I mentioned so I'm just showing you. Okay, two last slides, of course. We have a Erasmus agreement, so feel free just to visit Lublin. Yes, actually, Rohit and Asifa have been there, so I think they can recommend it, as you are also the employees of UCD, so you can just also use our Erasmus agreement, so you can come, of course. So in the middle of June, we have a staff week, so just feel free just to apply, and yes, in the moment you can visit us. So. The weather, the food, everything is so nice. So the culture there, so the worries is really affordable place worth visiting. So if it goes about some description, like about those two slides. So this is the rectorate of my university. This is the research center where there are many labs on site. So actually, I'm not sure if you have been there, but Rohit have been there, and actually he was amused by the airflow tunnel. So this is a big one, to be honest, where you can test the aviation structures, yes, inside. This is my former faculty of mechanical engineering, the biggest one by the building, and this is my new faculty of mathematics and information technology. So now I have pushed more to the IT from the land where I started. A couple of photos from Lublin. So this is actually the Krakow's Gate. This is the castle, medieval castle in Lublin. This is actually the city hall, and this is specific for Poland, that it can be recognized that we have a yes. Now there is I would say like a mode for electric buses, but those electric buses have been introduced even 50 years ago. So this is electrified one, as you can see over here. This is electrification of the system. So everything was electrified many years ago, to be honest. So it was quite unusual. But this is actually what Lublin is famous for such electrical tractions and those electric buses. I'm not sure if you are keen on football, but now we have 2 years ago, during visit of my Japanese colleague, actually after 33 years, actually Motor Lublin, the football team just got promoted to the first league again after over 30 years. This is actually also what we are famous for the speedway. So on the track, so those are the motors. You can imagine that those bikes they don't have brakes. Yes, really. So they are just, and actually Lublin was, Motor Lublin, that's the same name for the club, was 2 times, recently 2 times it was a Polish chap. Of course, it goes about when you come, for example, in the summer, even in the June, we have a lot of cultural events. Yes, not only for students but also for the whole city. So this is a, let's say, in the past it was a student city. Now it's still there. Okay.
That was a very interactive presentation.